Okay, shall we start? Can somebody confirm my audibility as well?
Yes, sir, we can hear you.
All right, thank you. Okay, on the last week we completed on the IP multicast, as well as we started on this thing, what's called the time synchronization and time stamping. And further, I uploaded your second assignment, and you will be having 3 week bit more than 3 weeks. So mostly the unicast, broadcast, and multicast, plus the time synchronization and time stamping tested on there. And again, in terms of, we'll be starting today on this introduction to network analysis, and I'll be running through a bit fast on this because you already covered this network analysis part by Wireshark based on the information received from Dr. Tarindu. And I'll be doing more of the advanced Wireshark stuff, including the packet capture and analysis setup description. So before we start on this is the agenda in terms of first session. We'll be starting with on the introduction and those sessions on different filters and the mapping with the OSI layering and all those stuff. So some part of the last week sections may be relevant to today as well. So further, I added few more slides for your additional reading and to make it more relevant to this particular session and the next session. So let me go back to the previous session, and further I uploaded an activity as well. So probably we can discuss that as well. Just allow me to go back and be described on what I added. Hope you can see the screen. Okay, let me recap quickly on the last week. We were discussing on the time synchronization and time stamping, and we had an initial discussion on the importance of time synchronization and time stamping, and the kind of modern day targets on the time synchronizations, especially based on the industries such as financial and financial markets, usually having certain regulatory target. So we were in the discussion of that part. And again, in terms of implementation of network time protocol, as well as the PTP protocol and the differences compared. Finally, the time stamping, and I'll be covering bit on how we discussed bit on the analyzing as well, especially on the ER span and nanoseconds time stamping there with the analyzing through the analyzing boxes while transferring to the remote nodes. So let's go back to the introduction. Here we were discussing on the different requirements on the service provider, especially with the dialogue and telecom. They are having precise time stamping and time synchronization implementations, and in industrial solutions such as assembly line and the production lines, which require synchronization of each and every step in the process. Otherwise, it is difficult to progress with the assembly line. And then the financing and the trading, financial market and tradings require strict guidelines or strict time synchronization requirements based on monitored by the regulators. And smart grid and electricity networks currently managed by the smart ways, like nowadays there are computing systems as well as artificial intelligence getting involved. These smart grids require precise time synchronization. And again, in terms of audio and video broadcasting, which is required for the multiple locations to be synchronized, or multiple if you're doing a live video broadcast, you need to synchronize with different locations, and the camera systems should be synchronized as well. So those the multimedia industry is using these accurate timestamps and time synchronizations to make it more productive, as well as to streamline the process. And the scientific discoveries and scientific computing mostly getting involved with this time stamping and time synchronization, especially the atomic collider in European region, which is named as CERN, is one of the initiators of this precision time protocol, based on the measuring requirements up to the nanosecond level accuracy. And the precision time stamp fundamentals, we discussed most the tie clock as one of the most important component of the electrical and electronic systems, including it's required for network diagnostic, application transaction monitoring, and data and event log analysis, and all those based on accurate requirement for the accurate time stamping. It's a mandatory requirement, right, for all the systems which you are planning to implement or which you have already deployed. You need at least some form of time synchronization, at least with the accuracy of milliseconds. Right, it's about synchronization and sequence and synchronization. So for an example, we discussed on this assembly line, certain things should happen with a sequence. For some of the processes are path dependent, which means you can't do second thing before the first one based on the sequence. For an example, let's say path dependency, we can explain such as, let's say, you are having washing machine. So if you can do, usually you are doing is first you are doing the washing and then you are ironing, right? If you do it other way around, like first ironing and then washing, you are not getting the expected outcome. Similarly, the sequence matter in the entire production processes or any other process. Sometimes there are situations like path dependency matter. In there, you need to maintain the sequence. So to maintain the sequence, you need to have time stamping to measure whether it is went through the exact expected time, expected sequence. So that's why you need timestamp to monitor entire process, whether it is electrical or whether it is production or something like that. So then about the synchronization. The synchronization require is because let's say we are supposed to start this session on 8:30, right? So if you are starting the session on 8:30, all of our watches should be synchronized. So usually usually at least with a precision of 1 minute or few minutes, we need to synchronize, because we have an agreement to meet or join this Zoom session on or before 8:30. So if let's say we have 20 different watches or among us, and we have variation with the variance of 5 minutes. So probably we are getting we need to tune plus or minus 5 minutes in terms of that. If we may, so that's the importance of requiring synchronization, the accurate same unique time or accurate time among us. The synchronization is important whether even you have the best clock in the world. So that's mattered, because you need to synchronize among for the joint work with the exact time or single time communicated among us. So synchronize all of our watches to the same time. Otherwise, somebody will join at 8 a.m., somebody will join at 8:30. somebody will join it after 9, or it will happen if you are not synchronized all of your clocks or watches. So similarly, the production systems or the computing systems, you need to synchronize all of your electrical equipments, including computers, end-host, and the network devices. All should be synchronized to the same time. That's the purpose of synchronization. Then if you are monitoring a flow, troubleshooting a flow, then you can use timestamp based on the synchronized with trusting all synchronized uh, to the same time, and one after another. Then you can start troubleshooting the application flows, the network flows based on the synchronized time, and you can get understanding of which event happened first and which one happened later, or is it happen within the expected time period or service level agreement. So those can be monitored, and it is quite useful in troubleshooting if it is necessary to your network or the entire IT system to synchronize to the same time. So those are the main requirement in terms of accuracy. You need to increase the accuracy of your timestamp by based on the requirement of sequence as well as the synchronization. All right. The previously on the first few sessions, we started discussing on these ultra low latency switches, and those are 190 nanoseconds port-to-port latency. Nowadays, we have the layer 1 switches. Now we have 4 nanosecond port-to-port switches. These are mostly layer 2 or layer multi-layer switches. And it is quite interesting that the numbers are getting low in terms of require the precision up to the nanosecond. The modern day electronic trading environments, nowadays, the trading not happen only among the humans, or the traders are not just representing the humanity or the humans. There are electronic trading going on. It is quite faster than human intervention, but the electronic trading venues usually expected in Europe and America to synchronize their network hops from edge router up to the first level servers. Data centers should be synchronized within 100 microseconds precision. But the ultra low latency venue, this number regulated as 1 microsecond. So that's the precision required for most of the financial market environments these days. So we should plan or aim on those numbers if we are targeting to implement time synchronization on those industries. So need accurate timestamp. I explained several things in terms of not precise time on the local clock not sufficient. You need to synchronize with all the other clocks, and you should have accurate reference clock as well. If you are synchronizing pretty much the weak or the cheap clock, then your drift will be higher, and it's not accurate. So you need a reference clock with the better reference clock than your the receivers of time. So usually the reference clock named as master clock in terms of NTP as well as PTP. So we'll be discussing that. We discussed several options in terms of the modern packet networks. We were using network time protocol for many decades. Now it's based on the time requirement and the goal. We should consider in terms of precision time protocol and its implementation based on IEEE 1588. The standard. There are the 3 variants so far. We are the version 1, version 2, and the version 3 is very much recent and not ready for the real world development deployment. Yes, because some of the most of the vendors are not supporting for let's say switch vendors and the network vendors are not supporting the IEEE 1588 version 3, but we are discussing here mostly IEEE 1588 version 2, which is based on the 2008 standard. So other two, other than NTP and the PTP, there is a global positioning system, GPS, with the satellites. So those are synchronized accuracy is 100 nanoseconds within the network. So iRig is another protocol used for the previous systems, which is somewhat the serial, not mainly for the packet network, but it's having the millisecond accuracy. So most of the time we are synchronizing the PTP or NTP grandmaster clock master clocks with the GPS systems to maintain the accuracy of 100 nanoseconds. Then you have the best reference clock if you are working for a global organization or something like that. So this is the version 1588 version 2, and it's having several characteristics. Mostly we are using Ethernet and UDP for the distribution of time, because it is possible to distribute with unicast as well, which means TCP as well, but by using UDP unicast as well. But it's mostly the best practice is on top of Ethernet, distributing by using UDP, with the multicast for the distribution and time correction. We can use the unicast for each and every clock, ordinary clock. So it is possible to implement by using this particular standard for the PTP. It is possible to make it accurate up to the sub-microsecond level accuracy. It's require low administrative effort because it is easy to manage, because we are using the same network engineering team and troubleshooting team for all the stuff, because we are using the packet network, not something proprietary. And it's low cost because you don't have to invest again for your time synchronization network with different equipment. So you're using your Ethernet network for the purpose, and you are using the same staff for the work. So it is supporting redundant and fault tolerance mechanisms by we are using the same techniques such as our network design and deployment. No need to implement costly dedicated timing network. That's the most important point there. And this was the hierarchy we discussed. The clock sources are mainly the master clocks. In here, even though you have two master clocks, they only one will be the grandmaster, and the master clock 2 will be synchronizing with the master clock 1 once it's become a grandmaster by an election process that is called bestmaster algorithm, bestmaster control algorithm. So once one of the clocks, even if you have 10 master clocks, the only one will get grandmaster and sending the time signal to all other master clocks for the synchronization. If the first grandmaster clock failed, then the second another master clock will become the grandmaster and do the function of active grandmaster. So that's for the failover. And then the second layer are the boundary clocks. Boundary clock mainly reside on the switches. So when you are purchasing switches, you should consider the boundary clock or functionality to implement there. So supporting 1588 version 1588 version 2 or beyond. Then the last layer are usually the servers or the endorsed. They are the slaves who are getting time from the boundary clocks. You can have two layers of boundary clocks, as in this example, two or many layers. So there will be time correction from the time getting from master clock for the boundary clock switches, and you are correcting the time and passing it to the downstream switches. And thereafter, the last switch, usually the access switch, the transferring, pushing the time to the slaves. And slaves are synchronized their system clocks on each and every machine. Also having cheap clocks, you are synchronizing with the boundary clock. Usually the grand master clocks and the boundary clocks having the better clocks with expensive clocks. But in host, usually the servers having cheap clocks or computers having cheap clocks. You need to synchronize by using PTP or NTP for that purpose. And these are some of the examples of time synchronization references. You are synchronized. Usually the synchronization comes from the bottom to top, because the clocks on the end host are the worst ones. So they should synchronize to the reference clock. Usually the packet traverse from top to bottom, which means master clock to the boundary clocks, then boundary clocks to the end host, which is ordinary clocks. So master clocks, as I mentioned, usually having the clocks with around say $10,000 or more, and having CCM or OBDM clocks, those are pretty accurate. So those are usually connected to the GPS network by having a simple small antenna mounted on the rooftop of your building and connecting to multiple satellites and getting synchronized within 100 nanosecond precision. So basically the ultimate time source will be, in that case, the GPS antenna or GPS system, which is based on satellite, connecting multiple satellites and getting synchronized. That's one of the best case implementations to make it unique and globally unique as well. If you're having multiple officers on different countries, it is quite required to synchronize with the GPS to maintain unique time among all the officers. And then you have synchronized master clock with the GPS. Master clocks are quite accurate. Even if you lose GPS signal for 1 day, the time error or time diff maximum will be less than few microseconds. So it is quite accurate even without GPS, because the drift is lower for this thing what's called grandmaster clock. You can have multiple grandmasters, as I mentioned before, but only multiple master clocks, but only one become grandmaster, and others are useful in case of failure of the grandmaster. Then you are pushing the time to the second level, which is the boundary clock mark here, which can be a boundary clock mark here by the green circle. And it can be forward to another boundary clock and synchronized with the ordinary clock, which are residing on your end host or the servers or the end computers. And it is also possible to directly synchronize some of the servers, directly connect to the first switch, which is the boundary clock. You don't have to always go through the two switches. Some of the hosts can be connected there. And the right side has different other notation other than boundary clock. It is called transparent clock. It is somewhat different from the boundary clock. Usually it is implemented with it was not there on the version 1, IEEE 1588 version 1, but the transparent clock implemented with the version 2, which is having less burden and most of the bypass of timing. It's possible with the minimum corrections there. So these are to support the previous generation of switches, which are not having accurate clocks sometimes. Then in terms of the PTP topology, I have more descriptions. When you are configuring the switches, or usually what you are configuring is the master clock connecting to the switch port. The master side will be the master port, and will be configured as PTP master port, and the receiving side usually configured as client port. That's how it progresses over the several switch layers up to the the end host or the ordinary clocks on the machines. So keep in mind the term of master port and the client port in terms of switches. So we discuss how the time synchronization happens with the synchronization between master clock and the slave clock with several message types. These are defined by the standard. You can see the several packet types: sync, follow-up, delay request, and delay response. So one of the assumptions here is you can only implement PTP accurately on the symmetric network, which is sending side and receiving side should be equal distance or the same path up and down. If it is asymmetric path, the accuracy decays. So this is one of the key assumptions there in terms of calculating the mean path delay and the variance of drifting and corrections based on the clock offset. So these are quite important in terms of if you're having asymmetric network path, it is difficult to implement PTP accurately. There are several new ways of doing that. For an example, let me go to the real world example. If you're moving towards, let's say, if you're traveling from, let's say, Dehiwala to Colombo, then you can be noticed that there are after the Vellavatha bridge, you have asymmetric path. When you are moving from Vellavatha or Colombo 6 to Colombo 1 or Colombo 3, the usual goal road can be followed. But when you are returning, you need to use duplication road. So that is a kind of asymmetric path. It is not the same lane directing to the Colombo side or Colombo 1 side, and returning path is something else. It's similar to that. There are asymmetric routing or asymmetric networking implemented for several reasons, but PTP is not the best candidate there. You may have to follow different ways to address that. So then again, PTP topology is the various PTP node types we discuss. And these are some of the additional slides for your deep understanding how you synchronize and among different ones. In this case, left side, you can see only by using boundary clocks, and what's happened on the transparent clock, which is based on the IEEE 1588 version 2, which is the transparent clock introduction. So this was the comparison between NTP and PTP. The NTP based on usually the accuracy levels of the millisecond level. But for the PTP, you can tune up to the less than 100 nanoseconds even these days with the connecting with the GPS system. You can get up to the 10 nanoseconds accuracy. The primary, usually the NTP works based on the layer 3 network, which is mainly the router. When you are synchronizing with the NTP server, usually you are getting through the IP internet protocol and getting at the time from the remote IP, which is the NTP server. It's running on top of layer 3. But PTP is capable of running through the layer 2 switches as well. The time correction is more accurate, and that's why it's providing you the accurate time compared to the NTP. Just go through all the comparisons. These are useful. There may be questions on your final examinations, and your assignments included some of the questions in NTP versus PTP. So this particular slide is quite useful for your answering. And PTP usually works as a pull mechanism, push mechanism. Usually the grandmasters are pushing time to the other masters as well as the slaves or the boundary clocks. So it's a kind of push mechanism. But the NTP is more of a pull mechanism. It's getting requesting time from the NTP servers rather than NTP servers pushing time to clients. You need to configure your client and request the time from NTP servers configured there. That's how, so that's one of the differences. So the performances we discuss, it's deviating for the NTP. You can see that offset of the few milliseconds, which means the y-axis is based on microseconds. You can see roughly around more than 2,500 peaks there, which is 2.5 millisecond. And you can see the drift is quite high for the NTP and not accurate based on the orange graph. The green graph, it seems to be very difficult to observe as well, which is based on PTP. If I expand on the PTP area, you can see that it is within sub microsecond level, or the less than 10 microseconds in terms of drifting. In this particular case, you can compare the averages to 63 microsecond average for the NTP, which is the orange graph, and the PTP graph having 0.14, which is 400 nanoseconds of accuracy for the average. So these are the 4 components required to deploy PTP end-to-end. You require Grandmaster clock, which is you can purchase it from vendors like Symmetricom, Spectracom, and all those different companies. And the thing is, there is no single vendor to provide end-to-end PTP. You need to deal with multiple vendors. The boundary clocks usually are residing in the switches, Cisco, Arista, and other, and NVIDIA and other enterprise switches having all these boundary clock implementations. You should, before you purchase switches, you are planning to implement time synchronization, better to check with the specifications of PTP support with the IEEE 1588 version 2 and 2 above. And PTP clients usually on the enthos tab, you can implement timestamping or the synchronization at the client level. Usually, if you are expecting hardware timestamping, you can purchase the network card SmartNICs with roughly around more than $1,000. So you can synchronize the network card, those network cards which are having hardware clock, accurate clocks, and synchronize there. Then thereafter, you have a boundary clock or the ordinary clock on your machine, and it's synchronizing with the network card time. That's the most accurate way to deploy. But if you don't have SmartNICs, still you can synchronize by the software time for the software synchronization for the software timestamping, which is somewhat less accurate compared to the hardware timestamping for the timestamps. So these are the components you require for the PTP end-to-end deployment. This is about the precise time synchronization. As I mentioned in this particular example, you are synchronizing with the GPS to the Grandmaster clock. Now there are multiple switch layers. Switches can be configured as transparent or the boundary clocks, and you are synchronizing with your data center or any other VLAN, any other server in the VLAN or the server farm. So usually expectation is synchronized within 1 microsecond, and you just need to select your switches and the devices accordingly. So this is an example of 1 microsecond time accuracy within less than 16 hops. Those are some of the regulatory requirement specifically for Europe and US or North American region. One of the standard famous among Europeans is the MIFID 2, that's require this 1 microsecond time accuracy for high frequency trading. and you can have maximum of 16 hops there. Okay, this is another slide I included, and it is useful in our discussion on today as well in terms of Wireshark or the packet analysis. There are two ways to get a packet capture for the analysis. The first thing is the passive taps, which means you are the left side representing a passive taps. Basically, you should have a patch code between your end user computer and or the server and connecting your switch directly by the cable. But if you need passive packet capture, usually these are called as test access port taps. So if you are configuring a tap, then you need two patch codes, at least two patch codes. In this case, you need T3 for the take it to the network analyzer computer, which is the Wireshark in this case. So if you are analyzing traffic, what usually happen is your computer will first connect to the one of the ports in the tap device. Then it will be then your switch will connect to the second port. So you are now occupied with two ports, one connecting to the end host, another connecting to the switch, which means you are previously directly connected to the switch, and now it's broken up to the your end host to switch path has broken to the two pieces or two patch codes. Now, one of the copies from these two ports will be forward to the monitoring port, which is connected there for the monitoring. So basically, you need a couple of ports and output port for the monitoring. So at least 3 ports on this test access port devices. So tap is one of the easiest ways to do it because previously the previous generation of switches were not supporting the mirror ports, because mirror ports require several control plane or management plane enhancement and computing power required there. But most of the time, previously we were having taps for the data centers for the capturing. So the left side, you can see the test access port. Still, people are using this because it is very accurate and not only a passive tap. And you are implementing passive taps on the important servers like database and all the other application servers for the monitoring purpose. So that is something I added. And then the modern day switches having something called switch port analyzer, span ports. So you can just copy any port traffic, whether it is transmission or TX or RX, which means transmission or receiving from this particular port. You can just copy it to another port, which is for the required for the analysis, and probably your analyzer connected there on the monitoring port there. So it is just sending a copy, whatever the transmission or receiving or both, to the monitoring port, and the monitoring machine will be capturing the traffic and monitored there. In this case, the Wireshark implemented on this particular receiver or the monitoring port machine. Any questions until this point? There may be questions for you, the final examinations on these topics, taps and span ports. And the previous diagram, we have been discussing on the same local port on the switches for the analyzer and the transmitter or receiving computer. So that's usually named as local span, because your monitoring port as well as monitored port both are on the same switch, same local switch. That's usually called as span port or switch port analyzer on the same switch. That is, if you are configuring span port, then means that means you are mirroring one port to another port for the analysis. And I included this particular slide as well to compare there is something called R span, remote span, which means if you are sending traffic from you are just monitoring traffic from one of the ports, but the monitoring machine or monitoring server or the appliance is on a different another network, which is separated on layer 2, not the layer 3. So then you are sending traffic to the remote switch, and which is connected to the that particular remote switch. So that's usually named as R span, which means remote span. So that's the idea behind. I included all together in a single diagram as well on top. For the comparison, you can see span only within the switch, and a remote span between the switches through a separated through L2 network. And then you can see there is something called encapsulated remote span, which is somewhat secure in terms of you are doing a security course. It's usually based on the GRE tunneling, generic routing and encapsulation. If you have another network or the monitoring port reside or separate the monitored port and monitoring port, which means the monitoring the packet capture required monitoring port, which is on the gigabit Ethernet 0/0 on the left side switch, and connecting through the layer 3 switch, layer 3 network to the remote site, or the same, it can be same site as well, but the two switches are separated from layer 3 network, and your monitoring device, so the monitoring appliance connected to the remote switch. So in that case, you need to, it can be a wide area network, it can be a local area network, it can be just as separated through internet. So you need some form of encapsulation or the security. This particular case, you are using GRE tunneling technology, generic routing encapsulation, to transfer the monitored traffic on this local switch to the remote switch separated by layer 3 network. So that's having additional header, which is GRE header. That's identified as ER span. That's the one we discussed on the last week. So basically, you are having span source here on the local switch, which is the host A. You have another host on host B. When you are communicating between host A and B, you need to monitor the communication between host A and B at the point of span source marked here, and you are sending timestamping and sending through a GRE tunnel or a GRE encapsulation by using ER span, and the remote device getting it, remote switch getting it, and forwarding it to the network analyzer, which is the span destination based on ER span topology. So this is the idea in terms of but you have an issue there, because you need to timestamp here more accurately and send it to the remote device, not timestamping at the remote device in the case. So it's important to timestamp on the particular the monitoring point or monitoring switch itself, rather than because it may change the time when you are moving the traffic for the to the remote device. So this is another example of implementation. You have GPS antenna connecting to a grandmaster for the sub nano, less than 100 nanosecond synchronization. Now you are connecting to the switch A, and you are monitoring any the host or the communication on the switch A, which is the source span port, and you are sending it to the central server, which is on another, it can be on another site, So it can be on Wireshark. So usually you can get many configured many switches as you want. In this case, switch A and B, both sending as span captures at timestamp on their switches and sending to the remote server, which is the network analyzer. So this is an example packet capture analysis by Wiresharks. Once you can see that ER span packet having the generic routing encapsulation, GRE encapsulation, GRE on this Wireshark identified it as ER span. You can see the other details on the expansion, encapsulated remote span packet analysis. That's ER span. When you further analyze, you can notice that accuracy of the timestamp is up to the nanosecond level. So this is an example of ER span packet, which is having the exact timestamps for your analysis. It's about budgeting, how far you can spend or invest on time stamping or time synchronization. You can just implement NTP for if you don't have a regulatory requirement or any other requirement, and you don't have a much budget. It's quite cheap, but if you have a regulatory requirement or if your management decided to make implement time accuracy, it's the question of budget. So you need to invest on different components here. It's up to you to decide how far you are investing on your time network or time synchronization and time stamping. Okay. Further, I included some additional slides on the PTP can be implemented on, we discussed on the multicast, the layer 2 multicast and layer 3 multicast and all those stuff. It can be, PTP is again on based on the TCP, you can consider it as one of the application level the TCP stack integration. So the PTP can be implemented on layer 2 as a layer 2 implementation or the layer 3 implementation in this particular case. If you are doing layer 3 implementation, you're mostly based on the UDP and internet protocol, which is on the layer 3. Transport protocol will be the UDP, and then the upper layer protocol is PTP. That's if you are implementing, then you need two different VLANs, which is one VLAN for the time sync, another VLAN for the data transfer on the same access port, which need to be configured. But if you are implementing it is layer 2, you don't have a separate VLAN for that, at least on the access layer. So these are the downstream components. You're on the link layer with the cables and all those stuff, and then the MAC layer at the layer 2, then the network card driver. All those are getting involved in the process. Okay, some of the examples of if you require hardware timestamping, these are the few AMD cards. You can get NVIDIA Smart NICs, so the AMD Smart NICs, and there are other variants as well. So this is an example. These are few examples of modern day AMD solar flare cards, Smart NICs, which are having the capability of PTP time synchronization support as it's mentioned on the specifications here. Then I included one appendix slides as well. In addition to PTP, we know that it's having the nanosecond level accuracy. Now the people are investigating or doing implementation of sub-nanosecond level accuracy, because modern day switches having the 100 gig up to the 800 gig Ethernet standards, as we discussed. If you're having large pipe, then you need to analyze the sequence because parallel processing is going on. So you need to have sub-nanosecond accuracy, which is picosecond level accuracy on certain cases with a large distribution of data. and probably the White Rabbit is one of the projects going on, or the implementations becoming famous now. Beyond, it's providing accuracy beyond the PTP, and it's named based on, I think you can see, I hope you can remember that the Alice in Wonderland, there is a rabbit there, White Rabbit. So the project White Rabbit having a clock there. The if you watch the movie or read the novel there, so probably uh, uh, you can recall that it's named as White Rabbit based on this the particular clock on the clock of the White Rabbit. Right, and additionally, there are other ways other than ER span. For an example, the switch vendor named Arista, they are using a competitor of Cisco. They are using mainly the manipulation of, let's say, trailer on PCP Ethernet or TCP header. So you can see how they are doing. These are some of the references if you are planning to implement timestamping by using Arista switches. They have their unique ways, or which are non-proprietary mostly. So you can read on that if you are planning to deep dive. So that's about it in terms of what I wanted to share based on the last week explanations. Any questions before we wind up on timestamping? And I included few questions on your listing as well, assignment 2 as well, and there may be questions in your final examination as well. Any questions? All right. Okay, let me go ahead and probably we can, I included this thing activity as well. Let me discuss bit on that as well. You can see it on the course web, which I uploaded there. Okay, the last week we had this activity 1. I'm not going to do it because we have a time constraint here. So we are having only 2 sessions on today, and the last session on next week. Not on the next week, after the next week. So this is another example of what we have learned based on the multicast and unicast broadcast discussions, and 2 questions are there on this. If I read the question, the Charit is a network implementation engineer in an enterprise organization. So basically you have the information that about Charit is an implementation engineer. Usually the companies having the design engineers, implementation engineers, and sometimes the troubleshooting and the network operations engineers separately. Sometimes all 3 functions handled by single engineer. So in this particular organization, enterprise organization, having an implementation engineer. So his job is a network implementation engineer. Basically, his job is implementing network based on the requirements. So he's configuring the network as well as implementing or connecting the network components. You are the senior, so consider you are the senior network troubleshooting engineer for the same organization. You are somewhat senior, but doing a different role, which is mainly operating as an ops engineer or the troubleshooting engineer. Charit was asked to implement IP multicast on the existing network, which is currently configured to support only unicast and broadcast. So currently their network only supporting only unicast and broadcast, but no multicast applications. After the initial multicast implementation, Charit was the implementation engineer for the multicast, IP multicast. So just I want to highlight this particular term, IP multicast. You can check the slides what I shared. I was mostly covering the area of IP multicast, internet protocol based multicast, which is based on TCP IP stack. But there are multicast implementations based on layer 2, which is not Ethernet based multicast or something else related, which is based on layer 2. We haven't covered that. It is beyond the expectation of this particular course, and we haven't covered on the service provider layer multicast as well. Mainly the coverage is based on the layer IP multicast. So basically the application planning to be based on IP multicast. So that's the assignment received by Charit to make it the current network only supporting unicast and broadcast applications, but you need to implement IP multicast for your IP multicast application to run in future. After the initial, so he did the initial multicast implementation, and he began Charit has began user acceptance testing with the multicast application users and the developers. So you need to after the implementation, you should hand over the deployment to your users and the application developers in this particular case, because developers getting involved because the applications is newly deployed. So you then at the UAT test, during the UAT test, users reported application performance issues. So multicast application having performance issues, users reported that. After verifying the users claim, users claim, then developers get involved, and they began troubleshooting the application from the application perspective. They informed Charit that some application users were receiving overlapping multicast feeds. Okay, some users getting the overlapping multicast feeds intended for different departments, which means you are receiving multicast which you shouldn't supposed to get that, because let's say you are getting multicast feed as an HR department user, but you are getting multicast feed which is nominated or assigned for production department or the engineering department or different department. Not only you are getting HR department feed, even you subscribe only to the HR department IP multicast group, but you are getting somebody else's multicast feed just by subscribing the particular multicast group. In other words, users were receiving multicast feeds that were not relevant to their department. Sometimes even through the department had subscribed to only a departmentally unique multicast group. Okay. Even though they subscribe correctly, and because the application users verified they subscribed on a correct channel, still they are getting different department multicast feed just by subscribing to the unique IP address on the assigned to the same department. Furthermore, multicast sources, which were server hosts, are different for each department. So still the data centers having servers, different servers for the each multicast group for the source, the multicast transmission or the source servers. So there is no issue on the source machines, which means they are correctly sending. So no issue. So the first question is first assignment is now you are now working as a senior network support engineer, and now you are trying to help Charit, right? He's the implementation engineer and is now clueless. Draw an example layer 2 and layer 3 multicast solution diagram for Charit. So you need to draw a diagram with the end users or the end computers. Those should be connected to the switches, and switches again connected to the data center switches. Data center switches or the server farm switches are connecting to the servers, so multicast sources. That kind of a diagram you need to draw here in this particular case. I'm not going to draw it. It's your assignment or it's your activity. So after you draw that, you can start the troubleshooting in terms of exact issue. So you did all the troubleshooting with Charit and everybody. After initial checks and troubleshooting process, the second question, you are able to confirm that the network design and device configurations are correct and consistent. So those are perfectly implemented, and all the configurations are as it is configured as expected, and those are consistent. No issue in terms of configuration or the deployment by Charit or the software teams or the development teams. So now, what are the possibilities? Considering multicast group IP address assignment as the remaining primary area of concern. So now the IP address assignment, so you now have a concern that considering multicast group IP address assignment as the remaining primary area of concern, what could be the potential root cause of this issue? Okay, probably I can give you 1 minute or 2 minutes maximum to tell me what is the what can be the potential issue if we are having different multicast group for different department, but only receiver subscribe for only one group, but you are still getting some the multicast from another group which is not subscribed. So what can be the issue here in terms of selection of multicast group addresses? So you can search on the overlapping multicast. You are receiving overlapping multicast even you are subscribed to the single IP group. Can you work? You have access to Google chat, or if you have chatbots, that's fine as well. Just do all the searching and give me the potential answer after 1 minute. Can you start? Somebody can confirm?
So, so the question was the assigning to same multicast address to two different sections. Am I right?
Yeah, user, basically receiver, subscribe only to the one multicast group. And the sources, multicast sources, which are the servers, are two different servers and sending to different groups. For an example, let's say you have a group address. Let me write it down. there is group address. You are subscribed to group address of 239.1.1.1, and somebody else has a different group, which is again on a 239 x dot y dot z. It is a different department. You only subscribe to your assigned HR group, let's say 239.1.1.1, but still you are getting the messages stream parallelly getting messages from 239 x dot y dot z, which is assigned to a different department. That's the issue in terms of this particular case. You are correctly subscribed to the 239.1.1, but you are getting multicast from different department, and sources correctly sending different sources having 239.1.1 and 239x.y.z. What can be the issue in terms of this particular case? That's the rationality I'm expecting how this is happening. And you should assume that all other configurations are correct, but except your selection of multicast group is the issue area of concern. Any other questions? Anybody else? Hope others are working as well. You will be getting your final examination questions, essay type questions with the marks more than 10 marks, similar to these type of questions. So it's better you ask questions if you have concerns.
So that issue will lead to the layer to Mac overlap problems.
Yeah, it can be a layer 2 mapping issue. So
And IGMP snooping issues also there.
yes, IGMP snooping is there, but the troubleshooting process has tested on IGMP implementation. It's fine as well. So no duplication, IGMP already disabled. So area of concern is only on the selection of multicast group.
And we have to ensure switch. Yes.
You're correct on the process because the first thing you need to check on the IGMP snooping, which is flooding the entire switch. Even it is just implemented, the IGMP snooping enabled because this is implementation engineer done a quite good job implementing, but the area of concern is only related to the IP address range. Takura, you were asking another question as well.
Yeah. And we have to say there could be incorrect multicast group mapping.
Yeah, it is correctly subscribed. You have different group. You are not subscribed to the incorrect multicast group, which is assigned to because you are only subscribed to one group, which is 239.1.1, but you are getting multicast from another group as well. Okay, what can be the another group in if you find the answer? Okay, let me do it. Probably others can get involved as well. I shared a few more slides included on the last week session. Just give me a just give me a small time to find it out exact slides. Yeah, you can further search as well. In terms of, it's about mainly related to the layer 2 and layer 3 multicast or the MAC address to IP mapping. There is an issue in terms of the mapping between the multicast IP addresses with the multicast MAC addresses, as we discussed in the details. Uh, okay, let me go to the I'll double check on the slides after this session. Maybe I haven't updated exactly, but I'll update. Oh, okay. Okay. I think I included in this thing. You can further research. So usually we have an issue in terms of mapping multicast IP to MAC addresses. The multicast IP version 4 have a, you can see that 224/4, the first 4 bits allocated for the network address for the multicast. You can start from 224 up to the 239 in that portion. The rest of the portions from 32, which is 28 unique bits available for your multicast grouping. So, but for the MAC addresses, I hope you remember the MAC address of my allocation of multicast usually starting from 010005E. Those are that's the first 25 fixed bits. These are allocated for the multicast in terms of layer 2. The last 23 unique bits you can play around. The first will be first allocate first 25 allocated for that. You can see the disparity between the layer 3, which is IP Internet Protocol, and the MAC layer, which is the layer 2, having a difference here. The layer 3, you can see you can get IP addresses of playing around 28 bits, but you are having only 23 bits to play on the MAC layer. So there is a shortage of multicast MAC addresses. We can't blame anyone because TCP/IP developed 50 years back, and all these technologies were not there on the 1970s. So the later, as I explained to you, the history of multicast started, usually the standardization start on 1985 after more than around 15 years. So these are some of the issues in terms of implementing these multicast protocols. Those are not perfect because there are issues something like this. So by default, you have limited number of MAC addresses to assign with a large pool of IPv4 28-bit multicast addresses. So in that case, you have overlapping address ranges. You are getting the same multicast IP address can have two different multicast addresses may have same MAC address. So at the switch layer, there is no switches are usually operating at the layer 2. They have no way to, the switches have no way to identify the IP layer information. So they are just forwarding or the IGMP, even enabled with the IGMP. If you receive the multicast destination MAC address, so the address the form of IP multicast, you need to forward to forward both the the feeds to the end users, because the multicast the MAC address is same for the both IP groups. For an example, let's say we discussed on 239.1.1, right? There are calculators on the web. You can search it around. You can calculate if you have if you selected a group address, a particular address, there is a definitely another one overlapping within the range. For an example, if you selected 239.1.1, as I explained in the example, it is having the same multicast for all these other IP addresses as well, starting from 224.1.1, 224.129.1.1. All these IPs having the same MAC address, and you are getting multicast. If you send multicast to the 231.1, and your HR department allocated with the 239.1.1, but your engineering department all allocated even with a different IP address, in this case 239.129.1.1, both whatever the machine subscribe for 139.1.1 getting the multicast feed from other group as well, which is from the engineering department, vice versa. Both the department are getting IP addresses of the multicast feed from other overlapping MAC address holder. So therefore, when you are assigning IP addresses to internal network, you should use something the IP to MAC address mapping in terms of calculating configuring it as non-overlapping IP address. So that is quite important to understand that. So this is the example. If you draw a diagram, you have a switch here. You have the router and the bunch of machines connected together. So one of the servers sending audio stream with the 224.1.1. Another server, video stream server, sending messages or video stream by 239.1.1.1. The switch does not read IP addressing. It's have the intelligence only on the MAC addressing. So based on the MAC addresses, both the audio stream and the video stream having the same MAC address. Here you can see that even though the IP address is different, due to the shortage of IP to MAC address mapping, this fundamental issue. So you are sending the packets to with the same MAC address, and switch will forward. Even audio only receivers getting the video messages as well. The video only messages subscribers are getting, in this particular case, the PC2 subscribe only for the audio, but he's getting video as well, and due to this the same MAC address overlapping for the different groups. Even it's same for the video only subscriber, which is subscribe only to the through 239.1.1. It's getting the audio as well. Similarly, that's the reason in terms of something, even if you implement it perfectly, you need to select exactly the correct non-overlapping IP ranges in terms of based on this multicast mapping issue. So let me I will be adding these 3 slides for your appendix, and most probably it's already added. I need to double check, so you can use these slides to do the activity. Takura and others, are you okay with the explanation, or you have concerns?
Yes, sir, we are okay with the explanation.
All right, you can search further in terms of this is an activity. You can use anything, the internet. There are calculators for the IP address to the MAC address mapping, and identify the overlapping addresses on the internet, which is created for the for the network engineers to use. Okay, that's about the activity. Let's move to the we can discuss on the past papers or the sample questions as well. Just give me a second. Okay, since we are reaching for the last few lectures, I thought of discussing bit on the example questions. So based on your final examinations, and these are some of the past paper questions I taken into for a discussion. The first, just let me expand further. Okay, hope you can see it now. One of the example questions, these are based on the lecture number 1 up to 6. The process of the computer network can be divided into small tasks and assigned into a particular layer in a layered architecture. There are several network models with different layered architectures. List down 2 such network models and provide a brief description on each. You're getting 4 marks for this is an easy question. The question asked on 2 different layered architecture models. You can go to the slides of your first 6 sessions. We have been discussing the details on the OSI layer model, which is from the physical layer up to the application layer. And there is another model which is TCP/IP model, or the DoD Defense of Department model. So that's having only 4 layers, which is the link layer, network layer, and the up to the application layer in there, merging top 3 layers on this thing what's called the OSI layer. So you need to explain the differences, and probably you can do a small diagram with the all 7 layers marked. So that's the requirement of having brief description, and you are getting 4 marks with this simple question. These are some of the questions, or you will be getting 4 questions, and some of them are questions like this. Some of them will be having scenarios like we discussed previously. Okay, hope this is quite simple, and there can be questions like this as well. So just give me a second. Question B. In the network switches, there are several forwarding techniques. Mention 2 of forwarding techniques and explain one of them. So you're getting 5 marks with this. The network switches should be having forwarding techniques, and mention 2 of them and explain one of them in detail. Okay, so you'll be getting 2 marks for the naming, just naming the 2 techniques, and 3 marks for the explanation. That's the usual division of marks. Anybody can name the 2 forwarding techniques, so you can type it on the chat.
So there's the broadcasting traffic forwarding to all ports. That means flooding to all ports. Uh,
But they
and
are still the question on the forwarding techniques,
uh,
not the models.
uh,
You need
Store
to,
and forward and cut through.
yeah, that's the correct one. So usually there, as this question mentioned, I haven't explained you in the slides. Question mentioned there are three main techniques. The one is the store and forward, which is famous among all the enterprise switches. And then for the low latencies, you can see cut-through switches are getting famous. And there was something called process switching. So there are other variants as well. Those are the main fundamental techniques. So you should name the store and forward and the cut-through switching, and you can explain one of them in the detail with the diagrams and how it's effective in terms of use cases. So you get 5 marks in this case. So let me find exact slide for that purpose. Just give me a few minutes, few seconds, because I'm just trying to. Okay, we have a slide for this. Hope people remember this particular slide on the, I think it's on the lecture 5 and 6 session. So you need to find out exactly the details of between store and forward, what's the cut through switching. So it should be there on your first assignment as well, I think. So if you are, you should consider the forwarding techniques and keep in mind the main ones are store and forward, what's the cut through switching. Let's go to the another question. Another example question. Okay, hope you can see the question C. The control plane, data plane, and management plane are three different planes available in your computer networks. Describe two of them with the task they performed. You get 8 marks. Just try for this particular case. So can somebody explain the difference between control plane, data plane, and management plane in a brief terms? We have been discussing the areas like software-defined networking and all those things defined on the slides there. Okay, let me share the slide deck with you. These are kind of a essay type questions, but just testing the theoretical understanding in terms of the areas. So this is about the same like lecture 5 and 6. You see the difference between control and data plane. Usually the forwarding path or the A6 circuits forwarding from one port to another will be through the forwarding path. But the forwarding decision taken at the control plane level, usually having address resolution protocol, ARP tabling, the routing protocol, having this control plane decision making process, and the MAC address learning or the MAC tables belongs to this there, the control plane. And store and forward, store information on the forwarding tables, which is L2, L3 can be on the control plane. The forwarding decisions primarily taken at the control plane. So this one slide is explaining and distribution of different planes. Usually the control plane and data planes are on the same device previously, and separation of control plane and forwarding planes were there, including the management plane highlighted here. That's the idea on the centralized controller, having the control plane at the central place and communicating through the protocols like OpenFlow. For the data planes are implemented on the end devices, which are the switches. And we are discussing software-defined networking with the infrastructure layer on the data plane, and control layer, which is having controllers for the control plane, and the another layer emerge with the application layer, which is the communicating through the APIs for the control layer, which is the software-defined networking based on fundamentals. We were discussing the virtual network function, network function virtualization thereafter. That's about virtualizing hardware appliances became possible to implement on the as software instances. So these are some of the things we discussed. Probably you need to have the knowledge to answer these questions. Just go to, hope everybody clear on that. You can follow the slides, right?
Yes, sir.
All right. Then the last question, question D. These questions are not made by me. Actually, these are some of the previous lecturers implemented the last year question paper that's developed by me, and probably you can find it from the course coordinators, or if I have it, let me upload it for your practices. When you, the question is, when you investigate network related application issue, you notice a considerable level of jitter in your network. So this is discuss jitter as a metric with explaining the potential measuring and identification tools, jitter avoidance and jitter avoidance best practices. So this is a essay type questions. You need to recall your memory on the matrices. So matrices we discuss. I think the bandwidth, throughput, latency, jitter, and two others. We had a very focus on the six matrices in terms of measuring the network. So you need to consider you need to recall your knowledge on all six matrices, and one of them tested here, which is jitter, and you need to explain what is jitter and discuss jitter as a metric with explaining the potential measuring and identification tools. Hope you remember the tools such as iPerf, or there are other variants as well, which we included, and jitter avoidance best practices, because some of the applications are not resilient to jitter. So probably you need to consider that. Usually the voice and video applications are can be affected with jitter. And there may be other applications as well. You need to discuss the best practices to avoid the jitter. So you get 8 marks just writing the details or your knowledge on jitter. Okay. Let me find if I have the slides on that as well. Okay. So, okay, hope you can recall the memory on this session 4. And we were having discussions on the six different metrics, bandwidth, latency, throughput, packet loss, jitter was the 5th one. So the question asked on the jitter, then the last error rate. You can see jitter explained on one of the slides with the detail and troubleshooting tools such as iPerf. And so those are the slides you need to go through. You're not always getting one tested. You may be tested with other matrices as well. Okay. Hope you have the bit of understanding. I am usually discussing the examples of example questions on the last few lectures to make you understand the requirement to preparation of the network and going through all the slides. So I'll be sharing these sample questions most on the course web, so you can go through the details and prepare for the areas of concern. Okay, let's let me start on the network analysis part. I'm going through a bit faster in terms of the introduction session because I had a chat with Dr. Tharendu, and he was telling that you all having the first year and then first semester and other sessions covered with the Wireshark. But anyway, I decided to go through with the introductions because you need to have the proper understanding or the fair understanding in terms of fundamentals rather than just practicing things. You need to have a fair understanding to before go into the some of the advanced topics related to this. So it's about the agenda is on it's about introduction to network analysis, and agenda is based on the Wireshark to analyze the network packet. Let me share the slides. All right, it's about introduction to network analysis, and we have the agenda of Wireshark to analyze network packets and protocols. Then installing Wireshark. These are the introductory topics I'll be covering pretty fast. Installing Wireshark and performing packet capture, the Wireshark user interface essentials, OSI layering based analysis, these are the few important topics. The tap and switch port mirroring we discussed today as well. Capture filters and the display filters. So there are two types of filters: capture filters and the display filters, right? So this is Wireshark. There were time we didn't have something like Wireshark to analyze the network. It's created on 1997 by Gerald Combs, the person you can see on the picture. So to troubleshoot network problems at a small, he was working for a small ISP, and then he wanted a tool to troubleshoot some issues. So he decided to build, there were no tools for the network analysis. So he decided to proper tools for his requirements. So he decided to write one. So he did one on the first one on 1997, and Wireshark originally named as Ethereal. So then now became one of the most popular tools available for the packet level analysis of the network and application protocols. We were discussing how on the packet capturing options, we discussed on the taps, the passive taps, as well as the span ports, R span and ER span. Now, after you captured the packet by taps, so by using it's called the span ports or the R span or the ER span, then you need to analyze. You need the analyzer, right? The analyzer is usually this thing, the Wireshark, famous among the community or among the network industry experts, and it is open source as well. So it's freely available to download. It's available for any operating system or the kernels. Extensive range of features, coverage over many protocols, not thousands. Now almost we are getting covered with almost all the protocols on the TCP/IP stack, and including the ones with the RDMA as well. What we learned on the high performance computing on previous lectures. The continued support and improvement made possible by contributions over 800 developers around. There are the full-time developers for dedicated developers, because it's kind of open source development process. And not only that, you can certify with the Wireshark certifications are there now. Wireshark Certified Network Analysis is one of the certifications. You can go to PSNV Test Center and certify even from Sri Lanka. And Shark, they have conferences as well now. The Shark Fest, the last year they had one on US. So you can see some of the pictures here or included on this slide. So installing Wireshark is pretty simple, and you can go to the site and you can install whatever it's on the Wireshark org, and it's available on all the operating systems, and you can customize as well if you're for the installation package. The Wireshark relies on something called WinPCAP, which is for the Windows, and libpcap, which is for the Linux, Unix, and Mac libraries to provide the packet capture and the capture filtering functions. The appropriate libraries installed during the Wireshark installation. If you are installing Wireshark, then it automatically on the Windows machines, you are getting the WinPCAP driver or the libraries, and the libpcap will be there for the Linux, Unix, so Mac machines or the operating systems. And you can see that example installation on the Windows machine. It's optional now to install the WinPCAP. If you are not capturing traffic on your particular machine which Wireshark installing, you maybe then you don't need to have this WinPCAP implemented. Probably you can untick this if you are just using your machine as the analyzer, not as the capture. So you can get packet captures from somebody else, and if you are just analyzing, then probably this may not required based on that's depend on your requirement or the use case. So WinPCAP, which is library needed to capture packet from network interface cards on your workstation. So if you are not capturing but analyzing on the captures getting from the another people or you are just troubleshooting the issues based on the packet captures getting remotely or the somebody else, then you don't need this WinCap driver. But if you are capturing your own traffic on the machine, then you need this particular driver to be installed when you are installing Wireshark. And so this is an example of capturing you are doing when you're doing first capture on your network. So just open Wireshark, you can see the network interface cards and just start the capturing. So that's quite simple. I think everybody knows that. Even you have the possibility of selecting if you have multiple network interfaces. For an example, a laptop can be having two different network, which is the local area wired network connected to the wire, and you have the wireless connection as well. So in this particular case, this machine has gigabit Ethernet network card, which is a wired connection, and further you are connected through the wireless network as well. If you have those two connections, then probably you can configure capturing only one of these at a time, because the capture file will be larger if you're doing capturing both. So if you have a concern on one of the interface for the troubleshooting, you can filter the interfaces by using capture interface selection. In this case, you can see it here on the first screen. And once you start the capturing, you just need to press start button after selecting the interfaces. Then you will be getting captured with several packets, and you can see it on the different planes. Okay, let me explain the plane or the display here. So you can see that the number 1 saying the title. So basically you are capturing now on the selected only the local area network. Now we are capturing on the local area network and Wireshark version mentioned there. And so these are the information on the title page or title plane. Then thereafter, you can see the menu with the different file, edit, view, go, and all the tabs are there. The selections are there for the analysis, statistics, telephony, and telephony for the IP telephony, and tools, internals, and this may be different for the latest versions, but this is where included when I'm preparing the slides. So main toolbar, you can see the main toolbar with the short forms of selections. Basically, we can use these for the analysis or the selections in terms of various functions. Provide a quick way to access the most useful Wireshark functions and are well worth getting familiar and using. So if you want to become a Wireshark expert, you can create these toolbar icons to make it faster for the certain actions on your preference. Then you can have display filters. So the filter, when you are filtering, so let's, for an example, if you selected to capture all the traffic on the local area connection, the wired connection, then you will be getting all the traffic there. But if you need to analyze only a certain type of traffic, which is related to the IP address of, let's say, 192.168.1.111, so you can consider, you can filter that by including a filter expression there on the number 4. So the next plane is packet list plane, which is number 5. This is about what are the packets you are capturing right now and the timestamp or the time it's captured, and the source, the IP, the source machine for the unicast or multicast here, and the destination IP address or the MAC addresses, and the protocol field nominated here, and the length of the packet size, and then bit more information in terms of the packet. Mostly application informations are listed here. And you can see the number 6, that number 5 is the packet list plane. You can see the number 6 is packet details plane, which means if you selected one of the packets, which means in this case, you can see the blue, it is selected on the top, the packet list pane, which is the blue, which is marked as blue in this case for the selection. And you can see the specifics on that particular the communication or selected packet. So in there are sub descriptions which you can expand. The first one you can see that the frame, then Ethernet, then the Internet Protocol version 4, which is the IP layer, and the layer 3. The first two layers are usually based on the layer 1 and layer 2. The frames are usually on the layer 2. And Ethernet 2 is another the sub layer in so on the layer 2, and again on the protocol is Ethernet 2. In this particular case, having all the MAC addresses included there in the description. The frame layer usually showing the details like the size of the frame, like 1000 less than 1500, which is maximum transfer unit or for the frame, and the particular interface. Those the low level details, it is closer to the exact network interface card name and the frame size, and all those the layer 1 or the 1 or 2, the most bottom layer details are on the top with the framing. And then the layer 2 Ethernet layer information are showing here with the MAC address, source MAC address and destination. You can see the layer 3 information on there with the Internet Protocol version 4, source IP address, the destination IP address. In this particular case, destination is an multicast IP address 239. Hope you remember the first assignment on first activity on the private IP ranges of multicast. And then user datagram protocol, which is UDP packet, and it's showing the application port port number, which is the source port number, and the destination port number. You can see the application layer protocol name as hypertext transfer protocol, which is HTTP. So those, if you select after you selected the specific packet on from the number 5, which is the packet list plane, and the particular packet details showed in the next plane, which is marked here on the number 6. Then the packet bytes pane. You can go into the details of the bytes based on hexadecimals for the finer details. The packet bytes pane, this selection section displays the selected packets content in hex bytes or bits form, as well as ASCII display of the data that can be helpful. Some of the troubleshooting have a requirement to go into the level of ASCII display or the bits form. So it is included here on the number 7, which is the packet bytes pane. Usually when you are capturing things on your machine, it's based on the bytes, not not after the serialization. The status bar, which is showing that where this packet capture file is saving, the location of your hard disk, and number of packets captured so far, and that is displayed here all the packets 396 and 100%. It's showing the drop packets. You can find out the drop packet percentage here. It can be having more details other than this. So it is quite useful plane in terms of the status bar, which is having the which is number 8. Having, you can use different profiles based on if you are doing the professional capturing, you will be having multiple profiles. We will be discussing this later. And just give me a few minutes. I will complete the introduction. So these are where you can have, you can see that you can filter your conversations by selecting selecting the packets. So the descriptions you can see easily on the even if you implemented name resolutions, which is DNS, you can see by the names. Sometimes it can be if you haven't enabled name resolution or name resolution, it can be seen on the IP addressing level. So if you need to understand the conversations on the local area network connection based on the packet capture, this is one of the useful features to display the different conversations and filtering it. And this is the you can see, just give me a second. Okay, you can see the name resolution enabled or disabled here by going to the view tab. And once you enabled name resolution, then you can see the DNS, see the conversations by naming conventions or the URLs. No, if there is no DNS enabled for certain machines, then you can see those conversations just by IP addressing. And you can implement the filter for the display based on the selections there. Once if you're applying the filter just to investigate between only two different hosts, both ways or one way, can be selected here by filtering by applying display filter. So display filter is something else compared to the capture filter. So if you are capturing only certain type of traffics, you can put a capture filter. After you capture or while you are capturing, you can check on put display filters just by using your selection here. By selecting one of the packets. In this particular case, address A is wireshark.org, which is and return traffic from Wireshark, which is the source address. And applying, you are selecting packet and selecting A to B. Based on this particular flow, you can select a source and destination and the traffic between two filtered by implementing filter in a display by applying display filter. Further, you can put an expression on this particular place, the filter location, which is number 4, display filter toolbar. Display filter toolbar can be having expressions based on the convention there. They display any packet that contains IP address and that IP address. If you have a couple of IP addresses, you can implement the filter, display filter in this way by selecting one packet flow, or you can just go to the filter and put the expression there by knowing the IP addresses. The expression convention, I can tell you that IP address, which is the source IP address, double equal means equal, and you can put the IP address, and which means you are matching the destination as well. So double AND is the convention for the AND, and IP dot address and double equals, then the destination address. So you can filter combination of these IP addresses for your display, for your analysis, because others are noise. You are just troubleshooting on this conversation between these two IPs. So you can, after the capturing, you can save the trace as well. Usually the capturing formats are different. The PCAP is the shortest form. Now the latest the Wireshark capturing having more different formats and having more different features on the each format. In this particular case, you can see the PC APNG is the format here, which we are saving the latest one. So that's about how you start capturing, applying the display filters. So let's move on the mapping between the OSI model and the DARPA layers, which means TCP/IP. You can see the 4 layers: the network layer, interface layer, internet layer, transport layer, application layer. So 7 layers you already know. So you need to follow these layering mechanisms to analyze. So for an example, you can see the destination MAC address, which is based on the hexadecimal, and source MAC address again on the hexadecimals. We were discussing the multicast group address as well on today. So MAC, then it is important to understand the different, hope you remember this first capture in this particular case. The Ethernet 2 details, which is the layer 2 Ethernet details having the MAC addresses, source and destination MAC addresses, especially the source address, which is a unicast address, and the destination is multicast address. You can recall your memory on today that filter in the multicast 01005E is the first 3 octets for the multicast. You can see it confirmed on the bottom layer, internet IP layer as well, which is 239.255, the multicast IP, private IP range. Similarly, in this particular case, you can see the different fields here. The important one, this is about Ethernet 2 frame. The Ethernet 2 frame sizes, the minimum size is usually 64 bytes. The maximum usually MTU, message transfer unit, we are configuring on firewalls, and the routers and network devices are usually, in this particular case, maximum is 1580 bytes. So we are configuring, we are having all these fields with the variance of size. Usually the destination MAC address field is fixed, right? You just need 6 hexadecimals to be included. Then the source is similar. Ether type require a few bytes. And usually the MAC header require 14 bytes, which is including destination, source, and the ether type. And still you have you can go up to the maximum of 1518, but 64 bytes comprise with the number here. So you can see the payload of datagram. It's having the layer 3 header as well, because that is the next layer, because now we are on the layer 2, which is on the Ethernet. So Ethernet header only having the MAC header is required only 14 bytes. So let's go to the next layer information, whether it can be IP packet or address resolution protocol packet, which is on the layer 3. And that's the payload for the datagram. And then that's including the data plus the next layer information. And lastly, there is a CRC check, cyclic redundancy check for the verification of packet authenticity. It's require 4 bytes. That's the trailer. So in the middle of this, you can play around. You can get Ethernet frame getting only 14 bytes. You can play around between 46 to 1500 bytes for this particular the Ethernet implementation. The jumbo frames are somewhat different. Just consider the basic Ethernet frame with the Ether type 2. So ether type field, this indicates the next higher protocol layer. Typically, it's identified as because if it is IP packet or the next layer, it's identified on this particular ether type. Because layer 2 information passed on to the layer 3 at the next step. So that's why we need this ether type defined on the MAC header. And the address resolution, if it is address resolution protocol, not the IP, it's require 80806. In this particular case, its ether type is 0800 So it's forwarding for the IP for the next layer. Wireshark uses this to determine next protocol dissector to apply in the packet decodes. Then payload on the next layer information plus the layer higher layer information and including the data. This packet or the data carried by the Ethernet frame. Based on for the Ethernet frame, the other than these first few headers, so the MAC headers, these are the payload or data. The frame check sequence, this is 4-byte cyclic redundancy check error detection code calculated from all the bits in the frame and added to the frame, which is the trailer. So understanding of the packet structure is important for your network analysis. All right, let's take a 15-minute break and we'll be meeting roughly around 11. So I'll be putting a timer on that. Then we can start discussing the details in terms of Wireshark further. Any questions before we wind up for the break? Okay, let's take the break now.